All right, good morning. Welcome back. It's more crowded during the midterm. Okay, space, the final frontier, as they say. Actually, it's just the second frontier in complexity theory. We talked a lot about time in the first class, the first half of the course. That's the main focus in complexity theory, but probably the second main focus is space complexity. Space is the old-fashioned phrase for like memory. It's like memory usage of algorithms. Okay, so for the next several lectures, 3, 4, 5 lectures, we're going to talk about the complexity of algorithms in terms of their space usage. And space and time, you could joke about Einstein or whatever. Are they the same? What's the difference? Well, there's a joke in complexity theory, but it's true. The difference between space and time is that you can reuse space. So that's what we'll see when we're talking about algorithms. This is like one key property of space that somehow makes it like more valuable than time in a way. Like having a certain amount of space is somehow a bit better than having the same amount of time. And you can really see this in algorithms in real life too, I think. For example, I think I read recently that Google announced that they finally found some collision in SHA-1, this cryptographic thing, and I think it took a program that ran 2 to the 60 many operations, which is a lot, but they managed to do it. So that's a lot of time, but I think if it required 2 to the 60 bytes of space, then they would be hopeless. I mean, this is really impossible to use that much space, whereas maybe you could potentially feasibly use that much time and get away with it. So I think space actually is a huge bottleneck in an algorithm. You can imagine it would be impossible for you to I don't know, if you wanted to write some web crawling app, just first download Wikipedia onto your computer and then run your algorithm on it. That would be kind of impossible due to space reasons. Okay, so that's what we're going to study for the next few lectures. So let's make a bit of a preliminary definition about space complexity. I mean, it's kind of intended to be the same as the definition of time complexity, just about space, memory usage. So here we go. The space complexity of a decider Tm. We're going to go back to Turing machines. As we sort of must. It's the only model where we can really 100% rigorously say what we're talking about. Well, just like the time complexity, the space complexity is a function, which maps an input length to the maximum space usage over all inputs of that length. Okay, so again, we're going to measure space as scaling with the running time. So let me call it capital S. And S of n is the maximum over all inputs x of length n of so space on Turing machines is the number of memory cells that are accessed. So the number of distinct tape cells accessed by m on input x. Actually, it just occurred to me when I was writing it, there's something a little bit weird about this compared with time, right? I mean, with time, thinking of it as scaling with the running time, you're like, well, I have a longer input. I'm just going to run my machine, my algorithm for a longer time. Here it's like, oh, I have a longer input. I'm going to need more space. It's kind of like you need to buy a new computer as the input length gets longer and longer. But nevertheless, that's how we'll analyze things. OK, so this definition is not exactly the final version of the definition. It's actually an OK definition, but it doesn't serve every purpose we need. So let me go back to the example I mentioned. If let's say you wanted to write an algorithm that, I don't know, crawled Twitter and did some kind of algorithm based on the graph of all Twitter followings relationships. Well, again, you wouldn't download it to your machine first, the whole graph of Twitter, and run your algorithm on it. You'd kind of treat that input, the graph of all Twitter users, as some kind of read-only input that you could access, but you would sort of only worry about how much computation space you were using on your local machine. OK, so we want to get at this possibility in the definition of space complexity, where somehow you're not charged for the input. I mean, most algorithms, if they're going to decide something properly, kind of need to read the whole input. And that's sort of why the least amount of time we ever considered was sort of linear time, because we imagine that it's not very interesting if the Turing machine cannot read the whole input. So if you're going to have a Turing machine read the whole input, then it looks like it's always going to be using at least space n. But somehow, it's not interesting to like insist on that. And there are very interesting algorithms that use a lot less than linear space. I don't know why I keep lifting this up and down. A lot less than linear space. But we need to change the model a bit so that we can talk about such things. So the way we'll do that when you're studying space complexity, you always focus on Turing machines with a special read-only input tape. I'll say what this means a bit more in a second. So when you're defining space complexity, your Turing machine will always have a special read-only input tape. Let me draw a picture. So this is the input up here. OK, and this is the input tape. OK, and then the machine is allowed to have like one or more work tapes. And these are just like the normal tapes that you can read and write on. So it's a kind of multi-tape Turing machine. And so this one will start out blank. And so as in multi-tape Turing machines, there's going to be 2 or more read-write heads. And we only charge in here for on the work tapes. So memory access is on the work tapes. OK, let me just for 1 second stick to one work tape. So just the model is the head can go back and forth here, and you can read the symbols here and decide what to do next based on what you're reading on the input tape. But you can't write to the input tape. You can read and write to this tape as normal, and we only charge you for your space usage down here. OK, so this gives us a nice way to be able to talk about algorithms that even potentially use less space than n. They can access the input to find out what it is. But if they only use a very small amount of sort of working memory, then that can be nice. And in fact, since we already got like more than one tape, I mean, granted they have different roles, we usually allow ourselves to have multiple work tapes. So it's like always, since it's already a multi-tape Turing machine, why not have a few more tapes if you want? I'll talk about why this doesn't make a big deal in a second. OK, so then the space usage is the sum of all the number of tape cells accessed on the work tapes. OK, any questions about that? So now, I guess based on this last statement I made that like, oh, it's OK to have more than one work tape, you should think to yourself, OK, well, I mean, does it really make a difference to the model? If I have a 5-work tape Turing machine, could I simulate it by like a 1-tape Turing machine? And if so, like how would that change the space usage? You might feel like you're too old to like go back to these details of like Turing machine simulations. But luckily, it's going to be a lot nicer with space than it was with time. So let me remind you of one thing we saw back at the beginning of the course. If you have like a multi-tape Turing machine, and you want to convert it to like a single-tape Turing machine that does the same thing, we imagined some way of doing it. You took all the tapes and kind of stored them in some format on the single tape, either interleaved or like serially. And then to simulate the multi-tape Turing machine, the single-tape Turing machine had to like kind of go back and forth and around to like remember everything that was going on. And so we had some property like if this one took time t, then this one took maybe time order t squared. But what's nice is, if you think about it for a little bit, if you kind of imagine what might go on when you do this simulation, let's say you have 2 work tapes and you're trying to simulate it with 1 work tape. Well, you can like take this work tape and just, I don't know, stick it out here with some punctuation in the middle. And as always with time, there's like some annoyance where, oh, if you kind of get to the punctuation mark, you might have to like copy everything over like one cell to make room for yourself and where you're storing the first tape, which is annoying for time. But for space, it's not really a big deal. I mean, that's fine. Essentially, you never really use much more space than you need to. So I'm not going to prove this, but I think it's easy to see that if a multi-tape Turing machine uses some amount of space S in total over all its tapes, when you do this simulation, I don't know, maybe there's a constant factor or a constant additive amount, but you can cram it all into order S space on a single tape Turing machine. So this really shows that it really doesn't matter if you're not worried about constants, whether you have one work tape or a constant number of work tapes. So in all this definitions, we'll just let you have, I don't know, any constant number of work tapes, and it doesn't affect anything. Does that make sense? So as we'll see, in order to rigorously talk about space complexity, we have to remember Turing machines again. But as I mentioned before, like somehow analyzing space on Turing machines is like a lot less annoying than analyzing time. OK, so once we have this definition of space complexity in place, we can make a definition of a complexity class for a given space bound, just like we do for time. So let me do that. So space f of n is a complexity class. OK, and it's just all languages, let me say A, such that there exists a Turing machine deciding A with space complexity. And as with time complexity, we're just going to build the big O into this definition. OK, so that makes us simpler to write. We can just write space n, let's say, for linear space. And also because we kind of want this big O built in for this reason anyway, so that it doesn't make a difference if we're talking about one-tape Turing machines, or two-tape Turing machines, or what have you. OK, great. So we just defined many new complexity classes, and studying these classes will be the subject of the next few lectures. Any questions so far? OK. So as I said before, kind of the least amount of time that we usually consider that's kind of interesting is linear time, because generally you need to like read the input in order to do anything interesting. Analogously with space, the sort of least amount of space that we ever kind of consider is logarithmic space, log n space. And one reason for that is it's not totally essential, but like almost every algorithm or problem that you're trying to solve, you would at least like to know what is n, like what is the length of the input. First step in algorithms often like for I equals 1 to n, do something. Well, you need to know what n is. And of course, to know what n is, you have to write it down on your work tape. And to write down n uses about log n bits. OK, so somehow it's essentially super rare that you would ever consider less than log n space for a relatively interesting algorithm. So log n space is the sort of least amount that we'll talk about. And let me just kind of state this fact. Using just order log n space. In fact, this could probably even be like log base 2 n plus 1 or something for what I'm about to say. A Turing machine on input x can compute what we would usually call n, the length of x. OK, and by compute, I mean like write it down in base 2 on its work tape. OK, and let me just say in words how to do this. It's pretty straightforward. So we only need one work tape. You can forget about this one. The head starts out here. OK, and the input, the read-only input tape's head starts out here. And what does the Turing machine do? It just moves the head on the input tape to the right, one step at a time. And as it's going, it just increments a counter down here. OK, so it starts at blank, which is 0, and then 1, and then 0, 1, and so forth. And when it gets to the end, which it can, let's say, recognize by when it hits a blank, then the counter down here will have n on it. You see, the Turing machine never really needs to use more space than log n, the number of bits it's eventually going to need to write down n. OK, because all the work is happening in here. I should mention, I think it's convenient. I didn't even think about it very carefully, but I think it's convenient for read-only tapes to allow the head on the input tape to have a stay put. So you can move it left or right or have it stay put. So that's convenient because in this algorithm, the head on the input tape will move along kind of slowly because we're doing a bunch of work in here. I don't even know how much time it takes, but for every step here, you need to increment this counter. OK, so that's good. So this motivates defining a very specific space complexity class, which will be quite important for us, which somewhat annoyingly is called L. Unfortunately, a lot of these complexity classes have annoying names. We already saw one-letter one on the midterm, E. I'm going to do another one here. L. This is just space log n. Okay, that's particularly confusing because we usually use L for a language. Now it's also a complexity class, but we'll have to get along. OK, so this is all the problems that you can solve using order log n space. And I'm going to give you some examples so you can get a feel for it. Because this is very little space, but you can still do some interesting things with it. Now, I guess counting the length of the input, computing n, is not quite in this class because this is a class of decision problems. OK, and computing the length of the input is like a function problem, writing down an answer. So technically, this is not in L, but something you can do in log space. Let me give you an example of something that a language you can decide in log space. So I'm going to try to use A for languages now. OK, this is like everybody's favorite language from the beginning of complexity theory. 0 to the m, 1 to the m. OK, this is the language of all strings that start with some number of zeros and then have the equal number of ones afterwards. This language is famous for not being a regular language, so it can't be solved by a DFA. But of course, you can solve it with the Turing machine in polynomial time. But we'll see, kind of better than that, you can solve it even with log space. So I will not write anything. I'll just ask one of you to say in words how you can solve this on a Turing machine with logarithmic amount of space. Yeah?
Count the number of zeros and then make sure that there's the same number of ones afterwards.
Give me a little bit more about how to make sure there's the same number of ones.
Well, you can decrease the counter as you go and make sure it's 0 again.
Yeah, that's the idea I had in mind too. Maybe there's other ways to do it, but I think the simplest way is the one that was suggested. You march OK, imagine you have some zeros and some ones here. You march the head on the read-only input tape along. And if you ever see, as long as you're seeing zeros, you increment the counter down here. And in fact, the number of zeros you expect to see is, well, it's never going to be more than the length of the input. So your counter will never get bigger than log n, where n is the length of the input. OK, and then once you start seeing ones, you start decrementing this counter, which again, you can do without using any excess space. You just decrement the counter in here. And you make sure that you don't see any zeros after that, just ones. And then you kind of just check that you get to the end of the input at the same time your counter gets back down to 0. And if all that checks out, you accept. Otherwise, you reject. Okay. Is that OK? Any questions? OK, so this was not the trickiest language in the world, but it is a non-trivial language. It's not a regular language, for example. And you can decide it with a small amount of space. Oh, I should have mentioned this. Notice that the algorithm, at the very beginning of this class, we talked about how to solve this language at all on a Turing machine. And there, the algorithm we used was not log space. Right? The algorithm we used there was, oh, you like start at the left end of the tape and like you mark that you saw a 0, maybe by putting a number sign on it. You go all the way to the end of the tape, and then you check that there's a 1 there, and you mark it, and then you go all the way back to the first 0 that's unmarked, and you mark it off and go all the way back, and you do this like zigzagging thing that takes n squared time. And that's not a log space algorithm. First of all, it doesn't even exactly fit the model, because in that algorithm there was only 1 tape, and you were allowed to write on it, which you're not allowed to do in this case. But if you wanted to do that algorithm in the model where you have a read-only input tape, the first thing you can do is just copy the input tape onto your work tape. But that already uses n space. OK, so as you'll see, I mean, the first algorithm you might think of, or the first algorithm we discussed for a problem, usually had time in mind, and it might not be the most efficient algorithm for space. Okay, so you have to sort of think differently about how to solve something in small space versus small time. OK, let me give another similar example using a super classic language from the beginning of complexity theory, namely palindromes. So here's a fact that we'll more or less prove. The language of palindromes, remember this is the set of all strings that are the same as the reverse, is in log space. And again, the most classic, if you're allowed multi-tape Turing machines, the best algorithm for palindromes, at least for time, is to just copy the input tape onto a work tape and reverse it, or otherwise have the heads at opposite ends, and then just march through the 2 copies, one in forward order, one in backward order, and check that they're the same. That algorithm is great. On a multi-tape Turing machine, it takes order n time, but it also uses order n space, because you have to copy the input. And we'll see now that you can do it with logarithmic amount of space. So what I'm actually going to show you here is first a solution that uses pseudocode, like in the more familiar algorithms writing model, because just like with time, we eventually want to get to the point where we're not literally analyzing Turing machines. So it's still early going, so we're eventually going to analyze Turing machines in order to reason about why this is the case. But I want to get you in the habit or the understanding of like how to pass from pseudocode to Turing machines and think about it in terms of space complexity. So OK, actually, if you were just a normal person with a normal programming language, how would you solve palindromes? Probably something like the following. You'd say, all right, on input x, depending on your programming language, you might not have to do this step. But let's say determine n, the length of x. And then you would do this probably, right? For I equals 1 up to n, just reject if xi is different from x. I guess I need to put n plus 1 minus I here. And then if you get through that whole loop without rejecting, then accept. Right, so you just check that the characters are the same in this fashion. And here, OK, we're going to go all the way up to checking the last character against the first character. We could have stopped halfway, but never mind. I don't even want to bother with going only up to n over 2. OK, so this is the correct algorithm. And let's now spend a little bit of time imagine how we would transform this into a Turing machine algorithm with an eye towards space complexity. And again, one thing that's nice is we don't have to be, let's say, frugal with the number of tapes we use. We can use 3 tapes, 4 tapes, 5 tapes if we like. I'm talking about work tapes here. As long as we use a constant number of tapes, it's fine. OK, so let's see. This part we already talked about, right? Well, this is going to be order log n space. And we can compute n on tape number 1, work tape number 1. OK, so the first segment of our Turing machine algorithm can do this, no problem. And now let's think about how we could do this on a Turing machine. I'll just start sketching the ideas here. We have like a variable here, a normal variable I, and it's going to go from 1 to n. And n is written down on tape number 1. So we can store I on tape number 2. OK, we can have a second tape. And we can really make a Turing machine that increments it up to 1 at the beginning and like basically has a loop that's like incrementing I at each stage and implementing the inside of the loop as it goes along. So since I goes from 1 to n, we only need order log n storage for I here. And you don't need really any extra space when you're incrementing a counter, right, beyond the total amount of space you're eventually going to use. OK. Now, let's take a look at this line. There's a lot of action packed into it. So one thing we're going to have to do is like look up the ith character of the input and also look up the n plus 1 minus ith character of the input. So sort of one thing we're going to have to do is like figure out what is this number, n plus 1 minus I. So I guess that's the next thing we need to do on the inside of the loop. So we need to compute n plus 1 minus I. And let's just do this on tape number 3. So we're in pretty good shape, right? N is written on tape 1. I is written on tape 2. I'm doing all this on like a new tape so that I don't want to like mess up n or I. So I'm just going to leave them sitting on their own tapes. And I can like copy them onto tape 3, for example, if I want. In fact, I might use another tape to do this. So here's what how I'm going to implement this. I'll copy n from tape 1 to tape 3. OK, this is again just some other subroutine in the Turing machine. It'll use, I don't know, 4 states or something, maybe 6 states, something like that. OK, but if you think about it, it's not going to use any more space than log n, the number of bits that it's copying. There's no need to use more space than that. Let's order log n space. And now I got to subtract I from it. Well, actually, I got to add 1 to it, so I can increment it. So now I've got n plus 1 written on tape number 3. And I was thinking about subtraction. And I think the easiest way to do it is like this. Just copy I from tape number 2 to tape number 4. So as I said, don't need to be frugal. Just copy it to tape 4. So now I have n plus 1 written on tape 3. I have I written on tape 4. And like n and I are still in the first 2 tapes, so I haven't messed with those. OK, now I'm going to do the subtraction. So I'll just do a loop where I repeatedly decrement on tape 3, sorry, tape 4, and actually on tape 3 too, till tape 4 hits 0. Okay, so I had n plus 1 up here, and I have I down here. I'm just going to do a loop where I decrement both of them until the one that started with I gets down to 0. And then I'll be left with n plus 1 minus I on tape 3. OK, you see I didn't need any extra space here, so I'm still in my order log n space budget. So now I have n plus 1 minus I written down, so that's good. So I mean, I have I written down. I have n plus 1 minus I written down. So the main last thing I have to show you is that I can do these like lookups into the input. I've got an index written down. I want to know what character x has at that position. So let me just show you that I can get out, let's say, xi. Using at most log n space. Oh, does somebody want to say how to do that? Yep.
Copy I to a new tape and then decrement and move right on the input.
Yep, that's right. So we can use like one more tape. So, copy I onto, I don't know, tape 5. And, make sure the input tape is at the beginning. And then, as was stated, repeatedly decrement it and move the input head to the right. One step for every decrement. OK, and then once you notice that your counter has gotten down to 0, then you're pointing at the right spot in the input tape. OK, and so you're reading xi, and you can write the value down on your work tape if you want. That's like one more tape cell, or you can just sort of store it in your state. That's a different way to do it. OK, and that's it. So you can see you can do like a lookup into the inputs in like no more space than it takes to write down the position that you're looking up. And of course, one thing I should emphasize here is that this is a loop that's happening n times. Like, don't like spawn like a new tape like every single time through the loop, right? You should reuse the space on this tape. Like, once you finish doing the lookup, you don't need that space anymore. You can reuse it on the next iteration of the loop. Okay, that's a simple but critical fact about space complexity. But you can do that. OK, that's it. So does it make sense? Great. So actually, I want to now try to just give you a mental model for log space. It's a very important class that we'll be studying for some time. So a mental model for it in terms of pseudocode. So in Turing machines, what is the mental model? Well, you just use log n space. But let's think of it a little bit about log space L in pseudocode. I put this a bit in quotes because I don't exactly want to write a theorem or anything. I mean, really, every time you analyze space complexity, you should really think in your head, like, OK, literally, how would I be literally doing this on a Turing machine, counting the space there? But to get the right mindset, I think here's what you should think. So here's some things. You can assume that n, the length of the input, is known. Right? Because your algorithm can have its first step, like compute n on some tape. That takes log n space. Now, in pseudocode, right, you typically have variables in C-like pseudocode, named like I or J or whatever. And like ints in C. And these are usually ranging, these are usually integers ranging in 0 up to n, or maybe poly-n. OK, or maybe like negative poly-n. OK, but that's what you usually have a variable holding, right? Like some number that's some integer between of the size polynomial in n. Not n bits, but like storing a number that's polynomial in n. OK, and these are all storable on tapes with like order log n space. Right, so if you're imagining converting pseudocode to a Turing machine. So what's interesting here is like, each variable costs you like log n space. So really, I mean, this is the main thing to keep in mind for L in pseudocode. It's really like you get a constant number of variables. Okay, you can kind of see that in this pseudocode. We have like, I don't know, 2 variables, like I and n. Or maybe if you want to think about this as like one more variable that you had to compute, that's a 3rd variable. So it's like an algorithm with like a constant number of local variables. And the mental model is like there's no array or memory allocation. Okay, you can't just say like, OK, like let's open up a new array of length n and put some stuff into it. Like that's, of course, can't do that. Read-only input lookups are a-okay. Right, because kind of as we saw, like, I mean, we're assuming you have log n space. You know, to like pull out any position of the input is fine. You can do that in order log n space. And as usual, kind of in pseudocode, like basic, you know, arithmetic operations on variables are okay. Right, you know, and then we did like basically n minus I, that was fine. Like it didn't cost us more than log n space on the Turing machine version that we eventually converted it into. Okay, so these are basically the mental rules you should have in your head for thinking about algorithms in L in like log space in pseudocode. But you know, it's a bit flaky. I mean, so you should always think carefully about how you would actually put it on the Turing machine, but this is what you can have in mind. So this is kind of the main thing to keep in mind. It's like an algorithm where like there's no memory allocation and just like literally a constant number of variables, like 10. So that handicaps you certainly, but I don't know, you can still solve palindromes like that. And let me just quickly say one thing about this arithmetic operations. You see, we actually did the subtraction in like a pretty weird way. Like you wouldn't normally do subtraction like that, even you know, if you're worried about time. We literally did it by like the first grade method of like subtracting like the number like one by one. And similarly, like imagine like, you know, A and B are variables, you know, so they're holding, you know, they're between, let's say, 0 and n, and you wanted to compute C, which is A times B. That's like, looks like a basic arithmetic operation. And why is it going to be OK in log space? Well, let's see. First of all, C itself is going to be between 0 and n squared. So this is, you know, 2 log n bits to write down the answer. So that's fine. You at least have enough space to write the answer. Now, if you think about the normal grade school method to multiply two numbers, okay, these dots are supposed to represent bits. So there's A, there's B. Okay, and then you write like times here. And, you know, you normally do this thing where you do this bit times this bit, and like you make this like tableau that's like shifted. Okay, and it has like, you get C down here. And it kind of has like one row for each digit up here. So it would have like log n rows and about like log n or 2 log n columns. That's like the normal way to multiply. But that's log squared n space. So that's bad. I mean, if you had to write this all down. But what you can do, instead of using like the, you know, the 6th grade algorithm to multiply, you can do like the 1st grade algorithm to multiply. You can literally just do this, like, you know, start out C is 0, and then for I equals 1 to B, C plus equals A. Just like add A into C, B many times. That's a very, very slow algorithm, which you should not do at all if you care about time. But if you literally only care about space, it's great, because you're basically just decrementing B and like incrementing C by A, and like you hardly need any extra space at all. So yeah, as I mentioned before, like if you are in the mindset like I only want to like analyze space complexity, minimize space, it's kind of fun because you start thinking about like algorithmic ideas you didn't think about before, because you know, once you abandon time, you can do a lot of like interesting things. So I'll try to give you some homework problems that are like this. For example, I think I'll put the following problem on the homework, so you can start thinking about it now, and it may or may not help you. Imagine you're given a list of integers, n integers, and let's say they're between 0 and n squared. Find the median. Okay, so like a lot of, you know, homework problems and algorithms are like, how do you do this in linear time? But now the problem is, how do you do it in log space? Don't answer the question if that's what you're about to do. No.
I'm asking, like, couldn't you just, if you use the 6th grade method of multiplication,
yeah,
you just keep track of, couldn't you just sum it every time you get a new, like, instead of creating the entire grid?
Yeah, you probably, I didn't think it through, but you probably don't actually literally have to write this all down. You could probably keep track of the results partially as you're going. That's true. But this is certainly the easiest way to do it, yeah. OK. So great. So I want to now, yeah, spend a little bit of time. I mean, Normally when people lecture about space complexity, they first jump into like polynomial space, and it gets into inefficient algorithms. But I like to study like the low amounts of space. Like what can we really do with like logarithmic space? So we actually saw we can do some stuff. So let's see what else we might be able to do. And let's start with the problems that we know are doable in polynomial time, like the actually efficient problems. And one great such problem is this path problem, ST path. And in the context of studying space, like this is like the most important problem in the world. Like it's so important to think about the space complexity of this path problem. Let me just remind you what it is. You're given a graph G and two vertices S and T. This is a directed graph. And these are vertices. And it's just such that there's a path from S to T in G. OK, so basically, I mean, in words, you're given a graph and two vertices, and you want to know, can you get from S to T inside the graph? Very interesting to think about the space complexity of this problem. So is this problem in L? So in light of this discussion about pseudocode, you should think like, OK, can I solve this basic problem with an algorithm that like doesn't allocate any memory, has a read-only input, and uses like a constant number of variables, like 10 or 100. OK, where a variable you can think of as like has enough space to like store the name of a vertex. OK, the n vertices. Seems a little hard. I mean, the first thing you would say is like, well, what about the algorithms I normally use, like breadth first search? I don't know. That's how I normally solve this problem. This uses more than log space. Because, I mean, the normal way to use this, do breadth first search, well, it involves at least, I mean, it has some other stuff. It involves like marking what nodes you've been to before, right? You like start at S, and you say like, OK, I can reach all of its neighbors. And you put like a check mark next to them or something to say that you can reach them. And you fan out from there. So you're not allowed to like write on the input either. So like you can't like, literally put a tick mark next to the vertices on the read-only input tape. If you want to do that, like store a bit of information for each vertex, you have to do it on a work tape. So this takes like order n space just for like keeping track of which vertices you've seen. You need at least one bit for each vertex to say if you've seen it or not. And the same is true like for depth first search. I mean, OK, you use different algorithms, but basically both of them have the property that they keep track of a flag, yes or no, for each vertex, whether you've seen it so far. So they certainly don't do it in logarithmic space. And then when you put it like that, it seems almost impossible, right? Like how are you going to tell if you can get from S to T if you like don't even have enough space to say which vertices you've seen before or not? I mean, you cannot allocate any array or anything. Like you got like 10 variables. Well, actually, we don't know if you can do it in log space, so that's tricky. But we do know one amazing fact. This is called Savage's theorem. It's from 1970, which is that this problem can be solved in space log squared n. OK, so not log space, but kind of close. Log n squared. So that's way, way less. I mean, it's exponentially less than n space. And we'll see this next time, next lecture. It's not very hard, but it's interesting. It's an example of like, you really got to change your mindset. If you're focusing only on space and you don't care about time, how can you do this path problem efficiently? In fact, the algorithm that solves this problem does not run in polynomial time. But it runs in log squared space. So you should think about this before Thursday. I mean, it's a really interesting problem. You proved it in the olden days, 1970. Like, it can't be that hard. Indeed, it's not that hard. Think about how you might do it. So if you want to think about it in like pseudocode, think about it as you get log n many variables. Or you can allocate an array of length order log n. That's how you should think about it. You can allocate an array of length order log n to help you out. OK, so we'll see that fact on Thursday. And I have to also mention this great fact. This is proved by Omer Reingold in 2004. The undirected version of this problem, same problem except G is undirected, is in L. So it's actually easier, well, seemingly easier. So that one, when the graph is undirected, you're given two vertices, S and T. You want to know, can you get from S to T? That one you can do in log space, like no arrays, just like 100 variables. You can figure out how to get from S to T if it's possible. In contrast to this one is super hard. I mean, that takes a long time to prove. It's a very sophisticated algorithm. OK. Any questions? OK, so actually it looks like things are going great. Like, seems like everything can be done. OK, maybe not in log space, but polylog space. Let's see some cases where it doesn't happen. Actually, one question you might have is, like, can you get ST path in log space? It's unknown. It's known that you can do better than this, but it's not known to get it in L. And this is a very interesting question. I don't know if experts have an opinion on whether or not you can get the directed version in L or not. Probably they think no, but not too confident. OK, let me mention another problem, which is kind of it's going to be kind of interesting in the context of space. This is a circuit evaluation problem. Remember this problem? Like, you're given C, a Boolean circuit, and X, an input. And you just want to find out, what do I get as the output bit if I plug this input X into this circuit C? Well, this problem is in P. You just kind of do it. You go through the algorithm, and like you just simulate, or the circuit, you just simulate it. You write down on each gate like what its output bit is, and that lets you figure out for subsequent gates what their output bit is, and so forth. So this is doable. If now let's suppose you care about the space. This is doable in linear space. Amount of space that's at most proportional to the input size. Because the algorithm, as I basically said, you can just go through all the gates and like figure out and write down what their output is. Okay, and to figure out the output of a subsequent gate, you look back at the outputs of the earlier gates feeding in. So you need even 1 bit of space basically per gate in the circuit. Can you do it better than that? Answer is probably not. So it's actually believed not in sublinear space. And we'll see reasons for that in subsequent lectures. But this is an example of a problem where we think you cannot do it in less than an amount of space that's proportional to the length of the input. And because somehow it seems like a very sequential problem. Like, you cannot, I don't know, save by doing things in a different order. The only way we kind of know how to solve this problem is like the most naive way. So that's a problem that you can do in linear space, but we think, for reasons you'll see, you can't do it in less. Let me do one more example. 3-sat. Can somebody tell me an upper bound on the space complexity of deciding 3-sat? If you got to solve 3-sat, you don't care about time at all, but you just care about space. What can you do it in? Yeah?
Just the number of variables, right? Like, you have a bit vector of their true values, and then you go through and check each clause.
Yep. So you can do this in order n space. And literally, you just use the most naive possible algorithm for solving the problem. Like, given phi, for each x in 0, 1 to the n, check if phi of x is true. And the key point, of course, is that in this, you reuse the space. OK, so you go through every possible string of length n, but when you go to the next string, just reuse that space. So you only need n bits to store this x. And then to check if x satisfies phi, I think you basically don't need any space. Well, maybe you need space to store an index into x. But it's pretty much negligible. So you can do this with linear amount of space, reusing this space. So this is interesting, right? Because I mean, this is an NP-complete problem. This is in P. So in terms of time, it seems they have very different complexities. But here, in terms of space, they have a similar property that you can do both of them with linear space. And this one we also believe you cannot do with less than linear space. Somehow it seems the space complexity of these two problems is the same. Yep?
So do we have any problems that we can solve in polynomial time that we can prove aren't in L? Or is that
I'll get to that in a second. The answer is no. OK. Any questions? Yeah?
Follow-up, is there a space hierarchy theorem or something?
Get to that too. The answer is yes. That's great. You're asking all the right questions. Exactly what is on the last 2 pages of these notes. OK, so let's, since we mentioned algorithms running in linear space, let's put a complexity class there too. And here, it's a bit weird because with L, we used exactly log n as our bound. And now I'm about to define this one for you, where we have polynomial factors. But somehow it's the most interesting way to do it. So here's a new class called P space. And this is polynomial space. So the union over all constants k of space n to the k. OK, so it's all the problems that can be solved with an amount of space which is polynomial in n. OK, so as we saw, this includes circuit eval. And it includes 3-sat. Well, and of course, it also includes all the other problems we've seen. So it includes path, because you actually only need log squared space for this. That's less than even n. It includes all of L, et cetera. So this is a pretty big class. It includes everything in 3-sat. It includes all these problems, including, for example, 3-sat. I will either prove this today, or it'll be on the homework, or it's very easy. So let me just state it for now, say as an exercise. Now that I've shown you 3-sat is in P space, it actually follows that all of NP is in P space. You have to think about that a little bit. We know from Cook's theorem that for every language in NP, there is a polynomial time reduction to 3-sat. And we know that 3-sat is in P space. It does follow then that every language in NP is in P space, but it takes a little bit of reasoning, which I may do if I have time, or you may do on the homework, depending. But you see, I just want to make the point that P space is a very big class. It contains all of NP. OK, so we've got some classes here. We got all space classes, and we've singled out 2 of them as particularly interesting: L, logarithmic space, and P space, polynomial space. So let's finally, do some basic relationships here. Yeah.
Is it true in general that if you can do it in non-deterministic time, then you can do it in the same amount of space deterministically?
Yeah, we will. That one also might be on homework or something like that. But yeah. So what I want to talk about exactly now is the relationship between space and time. But we won't mention non-determinism. Although, as we'll see in later classes, non-determinism in the context of space is very interesting. It's somehow different has a different feel from non-determinism in the context of time. OK, let's look at basic relationships between space and time, since we studied time so much. The first one is quite simple. The complexity class time f of n is a subset of the complexity class space f of n. That's the claim. Just in words, what does this mean? It means if you have some language in this class, then it's also in this class. So if you have some language that can be solved with f of n time, then you can solve it also with f of n space. In fact, if you have a Turing machine M that solves the language in f of n time, that same Turing machine will also do it in f of n space. Why is that? Yeah.
Because it's only accessing at most f of n like tape cells. So
That's right. If you have a Turing machine that runs in f of n time, it only has time to reach f of n different tape cells. So any f of n time algorithm is also an f of n at most space algorithm. Okay, so this is why, like I said earlier, that somehow space is in a way like more valuable than time. I don't know about exactly phrasing it that way, but for example, we now know therefore that P is a subset of P space. Polynomial time is contained in polynomial space. So here I mention an even stronger fact that NP is in P space. And we know that P is in NP. But actually, I guess in order to show this, you need to at least first make this observation. OK. So in fact, from this, it's actually, if you could make the same argument about non-deterministic machines and conclude that NP is a subset of NP space. But, well, it's also easy to prove this. OK, so that's the simple relationship between space and time. There is an opposite relation, but it's a little trickier. So if you have a small space algorithm, how can you be sure that it doesn't take up too much time? It's not so clear, right? It uses a small amount of space, but it could go on for a really, really, really long time, presumably. Maybe it could go on for like an arbitrarily long amount of time, you might think. But here's the, let me start it on a new board. Here's the theorem we'll prove about this. For example, one consequence of the theorem that I'm about to state is that L, logarithmic space, is a subset of P, polynomial time. So you might think to yourself, well, if I have pseudocode that only has a constant number of variables, no memory allocation, why does it necessarily run in polynomial time? It's actually not super obvious. I mean, what you're going to say? It's easier to understand on Turing machines, but yeah, what's the reason?
The fact you only have like a finite, you only have an exponential amount of space you use, number of different configurations. So if you run for more than that time, by pitch and call, you have to repeat the values of all the variables or the configuration of the Turing machine, which means you're looping. And since you're a decider, you don't do that.
Right. Let me write all of that down. So here's the more interesting relationship between space and time, which is for any bound f of n that's at least log n, which I mentioned is basically the only bounds we care about, space f of n, you can put a time bound on it. It's a big one, but it's exponential in f of n. OK, so for example, as an example consequence of this, if I take f of n to literally b log n, then I get that L is a subset of 2 to the order log n is polynomial, so polynomial time. And also, if I take f of n to be any polynomial, then this will be any exponential. So I'll get like p space is a subset of exp. This is exp time. OK, I'm going to prove this theorem. Any questions about it before I get started? OK, so as was mentioned, what is the idea of the proof? The idea of a proof is, I mean, imagine you have a Turing machine and it runs in some small amount of space. Think of f of n as small. Then basically, if you imagine its configurations, or if I had to ask you, like, at any given moment in time, like, tell me everything I need to know about this, the state of affairs with this Turing machine's computations so that I can figure out what happens next, well, you pretty much just need to tell me what's written on the tape, of which there's at most f of the work tape. There's f of n symbols. There's something like constant to the f of n many possibilities for that. You need to tell me where the tape heads are. You need to tell me where the read-only input head is pointing. But basically, there's going to be at most this many different possible overall configurations of the Turing machine. And then the observation is the Turing machine can never go to any configuration more than once. Because if it's at some configuration and runs for a while and comes back to the same configuration, and by definition, it'll just keep doing that same thing over and over, and it'll loop forever. So you can only go through each configuration at most once. So assuming you have like a halting Turing machine, it can only use this much time. OK, so let's say that in words. And in fact, we have to get this notion of configuration understood. It's very important, not just for this theorem, but for other theorems too. So, right. So let's say we have M decides language A in f of n, order f of n space. We want to show that M, not just that there is some machine that decides it in this much time, but M itself takes that much time. OK, so if you remember way back when we were studying Turing machines, we had the definition of a configuration. And the configuration for a one-tape Turing machine was everything that was like a string that was like the entire tape contents, plus you stuck a symbol for what state you were in into the string, and you stuck that symbol like right where the tape head was pointing. So somehow it encoded three things: where the tape head is pointing, what state the Turing machine is in, and what are the contents of the tape. Let's assume, without loss of generality, M has just one work tape. That's fine. Remember, we said you could reduce to that case easily. But it also has like one read-only input tape. And we're going to introduce a new definition of configuration that's suitable for Turing machines with a read-only input tape. OK, so I'm basically changing the definition of configuration for when you're talking about Turing machines that have this special read-only input tape. OK, so for such a TM, M, let's define the configuration of M on input X as you say a configuration of M on input X as, and notice that X is part of the definition here. So by the way, here's the picture. Here's input X. That's read only. And here's the one work tape. We'll have some, its head is at some position on the input tape and some position on the work tape. So basically, it's going to be the usual configuration of just the work tape contents plus the state of the Turing machine plus the work tape head position OK, so let's imagine this is like a snapshot of what's going on halfway through the computation, and M is in state Q7 or something. So then, so far, we would have like the usual configuration would be like this string WORK. I forget how we did it. I think maybe Q7 came next. TAPE. So that tells us the contents of the work tape, what state the Turing machine is in, where the work tape head is pointing to this T. The one thing that's not specified yet, which we still have to specify, is where the read-only input tape head is pointing. And one thing to keep in mind is we don't have to specify the input, because we're defining the configuration with respect to the input. So the input is considered fixed. The only mystery is like, where is the input tape pointer? So we're going to define it all like this, plus just an integer, the input tape head position. And we'll just say that we'll like stick it at the end with like a punctuation mark. So semicolon, and then this is at position 1, 2, 3. Maybe I should write it in binary, but whatever. OK, so the exact format is not super important, but the main thing to remember is the configuration when you have a read-only input tape with X written on it is just the usual configuration of the work tape plus just the position that the input head is looking at. And the key observation, let me not write it, but just say it in words, is this really encapsulates everything, like the snapshot of everything you need to know about the computation of m on input x at a given time, in the sense that once I tell you all this information, you can tell me exactly what will happen after taking one step and like what the new configuration will be after taking one step. Okay? It all depends on what state you're in, what symbol you're reading, which you can tell from this. It depends what symbol you're reading from the input tape, and that's just the third character of x. And again, x is considered fixed throughout the whole definition. So now let's make this observation about the fact that you can't repeat any configuration more than once. Let's make it a bit more carefully. So key point 1, m is a decider. So therefore, it never loops. It never gets into an infinite loop. And therefore, it can never repeat a configuration. So as I said, configuration tells you everything you need to know about how to continue the computation. If m is going along and hits some configuration c, and then it keeps going and hits c again, it's deterministic, so it'll just repeat this path of computation indefinitely. And it would loop, which is a contradiction. So therefore, the running time of m is bounded by the number of distinct configurations. OK, so we just have to now count that. All right, well, let's count it up. So this is the most expensive part. We have to count all possible work tape contents. So that's basically cardinality of the work tape alphabet to the power of f of n. Because it never uses more than f of n tape cells. And each one can store a work tape character, a tape character. But this is like a constant. This is some constant, like 100 or something. So this is where the exponential in f of n is going to come from in the theorem statement. OK, and we have to also account for the number of states that the Turing machine can be in. So that's, I don't know, we wrote that like this. Q is the set of states. But again, m is just some fixed Turing machine, so the number of states it has is some fixed constant. OK, and we have to account for the work head tape position. Well, that's not too bad. That's at most f of n. Maybe 2f of n if you imagine it can go left or right on this 2a infinite tape. But let me just say f of n. I mean, we already have exponential in f of n here, so this factor is kind of not very important. And there's one more thing to take care of. You have to store the position of the input head. And that's n. So this is constant. This is f of n. This is exponential in f of n. This one's a little annoying because you cannot obviously write it in terms of f of n. But this is where this assumption in the statement of the theorem is going to come into play. We assume that f of n is at least log n, because we kind of don't really care much about less than log n space. And so if f is at least log of f of n, this is already constant to f of n. This is already like exponential in at least log n. So it's at least polynomial in n, which is already way bigger than n. So we'll just make the observation that this is, at most, 2 to the f of n, because f of n is at least log n. Okay, it's just saying that this term is kind of negligible. So if you multiply this all up, you get some big constant, c, to the power of f of n. Okay, which we might also write as 2 to the order f of n. Okay, so it'll never use more than exponential in f of n time. Okay, so m runs in, let me just say in words, we prove that m runs in at most this much time, and it decides a. Therefore, a is in the class time 2 to the order f of n. Any questions about this proof? Okay, so don't forget about configurations, because we'll need to reason about them even in later proofs about space as well. Okay, so good. So we have some relationships between space and time. And let me now draw a picture of summarizing everything that we've figured out so far. So we've seen a picture like this before, and somehow in this class we just keep adding to it as time goes on, a picture of more and more complexity classes. So let me try to draw it here. Okay, the biggest class that we've sort of talked about so far is exp, exponential time. Okay, and then we just saw that p space is contained in this. Currently, we don't really know the relationship. Maybe they're equal. Actually, whether or not they're equal is unknown, but they're believed to not be equal, so I'll draw them as if they were not equal. Okay, and by this simple fact, it's still out there. P is a subset of p space. So let me put p in here. Actually, as far as we know, p could equal p space, but we believe they're not equal, so I'll draw it as if they aren't. We also talked about NP, so NP contains P, and we mentioned it's contained in P space. That's NP. And I hope you remember before the midterm we also talked about co-NP. It's not too hard to show that it's also contained in P space. The brief hint is that P space is close under complement. Great. Again, these could all be equal. Actually, there's two on the board that cannot be equal. We know by the time hierarchy theorem P is definitely not equal to X. So P is smaller than X. And then inside P we have L. Okay, so these are all complexity classes we've talked about so far. Oh, we mentioned a few others, in fact. Good. So actually, let me tell you a little bit about what we're going to, I'll say a few more things about this picture, but let me tell you what we're going to start doing in the next couple of lectures. One thing we're going to do is explore non-determinism in the context of space. So, we start out life studying polynomial time and exponential time, but it proved to be very fruitful and interesting to study NP, right? I mean, this gave us a lot of insight into the complexity of algorithms problems by introducing this notion of non-determinism. And equally well, it's going to give us a lot of insight into the complexity of problems by studying non-deterministic complexity classes, such as space classes like NL, which we'll see next time. And as we'll see, like somehow non-determinism is less powerful, seemingly, in the context of space than time. So we'll talk about that, and it'll give us maybe some insight into non-determinism. And the other thing that we're really going to try to do is sort of find a problem that's in each of these spaces here. We'll sort of capture each of these classes. So assuming they're not equal. So we sort of did that before, right? We were like, OK, well, 3SAT is a very interesting problem that's, yeah, it's in NP, but not in P, we think. OK, so that was very nice. It gave us an example of something to keep in mind, something that's in NP, but not presumably in P. We don't know for sure. For co-NP, we had tautologies. And we're going to try to do that also for space. So for example, put palindromes in here. That's some fact we learned. it's interesting to try to find a problem in here, something that can be solved in polynomial time, but for which we believe cannot be solved with logarithmic space. And we'll eventually see this circuit evaluation problem is a good example. So it's in polynomial time, but it doesn't seem like you can do it with a small amount of space. It seems to really need a polynomial amount of space. We're also going to spend some time trying to find a problem here. I won't even say what the problem is yet, but we'll find a nice problem that you can solve with polynomial space that we don't think you can do with polynomial time. In fact, we don't even think you can do it in NP or co-NP. And we also are going to know some problems in here too. But this is sort of what we're shooting for. We'll talk about maybe these two problems. And let me mention one more thing that came up, and that'll motivate us for the next lectures too. So we saw so far that L is a subset of P, is a subset of P space, is a subset of X. And we know, actually, for a fact, that these are not equal by the time hierarchy theorem. So these two sets are not equal. Therefore, P space, which is in the middle, has to be different from at least one of them. P space cannot simultaneously equal this one and this one, otherwise they'd be equal. So therefore, either P does not equal P space, or P space does not equal X. So we know that the or of these two statements is true, but we don't know if this one is true, and we don't know if this one is true. So it's still unknown. Either of these could be true. We just know they both can't be true simultaneously. In fact, we think that neither of them is true. But that's frustrating. And in fact, the same situation holds here. So there's a space hierarchy theorem, which I will state for you in 1 second. That's going to prove that L and P space are different. Space hierarchy says the same thing. If I give you like noticeably more space, you can actually solve more languages. So if I give you polynomial space, you can solve more languages than if I give you logarithmic space. And that shows that either P differs from P space or P differs from L. We actually believe both are true, but we can't prove either of them. OK, so basically the last thing I'll do is state the space hierarchy theorem. And it's basically the same as the time hierarchy theorem, only a bit easier. So it goes like this. Let f of n be a space constructible function. And what is the definition of that? It's basically two things. F of n has to be at least log n. That's similar to the time constructible thing where it had to be at least n log n. And you should be able to compute in order f of n space. This is exactly the same kind of condition as time constructible, but with the space bound. And it's because in the proof of this theorem, you again have to have a universal Turing machine simulating a Turing machine running in f of n space. So the universal Turing machine has to at least figure out, like, what is f of n. So it has to be able to compute the amount of space it's going to be simulating for, just like in the time hierarchy theorem. But there's an advantage, which is that if you have a universal Turing machine simulating another Turing machine, there's some kind of slowdown in terms of time. Like if the machine you're simulating runs for f of n time, then maybe it takes f of n times log f of n time to actually simulate it. But with space, everything is nicer. You can simulate it in basically the same amount of space that it actually uses. And that lets you actually even get an easier and simpler space hierarchy theorem, which I will just state for you. The proof is the same, but easier. And there exists a language, A, in space just space f of n, that's not in space g of n for any g of n which is like little o, if you remember that definition, of f of n. So basically, whenever g of n is like, this means that g over f goes to 0. So noticeably less than f. So there's no extra log term or anything. It's sort of as nice as it could be. And so for example, if you take f of n to be log squared n, and g of n to be log n, you conclude that there exists an a that's in time log squared n, but it's not in L. Okay, so if I give you log squared space, you can solve something that you can't solve with log space. In particular, this a is in P space. Okay, so the space hierarchy theorem holds equally well. And it tells us that, for example, L is different from P space. So we know that either P differs from P space or P differs from L, but we're not sure which. OK, I'll stop there and see you on Thursday.